Hey everyone, Morgan here. So we're going to be talking about molecular geometry today and the different ways that we can arrange atoms around a central atom in a molecule. We're on page number 6 of the outline. Now, if we take a second and we jump back to page number 4 and the molecule H2, which was a diatomic molecule, or the molecule Cl2, okay? Both of them basically looking the same, or even with the double and triple bonds, the O2 and the N2. What we're talking about is what we're going to call a linear molecule. Now, this molecule has two atoms, neither of them central, okay? It's a straight line, 180 degree bond angle. Let's put that in there, 180 degrees, okay? Now, this can exist with two atoms that are the same. It could exist with two atoms that are different. Okay, it's fine like that also. Or even three atoms. And it's a little bit different with the three-atom version in that you have one atom in the middle and then two substituent atoms, which are probably different than the one in the middle. Not guaranteed, but probably. A good example, this would be carbon dioxide. Now, any way that I look at this, it's a straight line. It's 180 degrees. Now, I'd really like to have the school district send model kits to all of you. I think it'd be more valuable even than a textbook, okay? But they're not going to do that. So, what I might suggest is that you get something that is a soft candy. Marshmallows, gummy bears, gumdrops, okay? Not M&Ms or Skittles, that won't work. And you get some toothpicks. And you can build these models the same way out of that soft candy and toothpicks. Marshmallows work real well because you can get different colored ones. So this is our first molecule, an A2, okay? That's the first geometry. Now, our next possibility is what we would call an Ab3. Now, an Ab3 has one atom in the middle, which is brown in this model, then the three substituent white ones. Okay? The angles in here are 120 degrees. It's a circle divided up three even parts. Okay? Now, if we go back this time to page number 5, you will see BCl3 was a good example of what that might look like. Okay? Now, one thing that's incredibly important about this is the fact that it's flat. It is perfectly flat. If I try to put my pen underneath it, that won't work. So some people call it triangular. Some people call it triangular planar. I kind of like that name best. And some books even just call it planar. I'm not very fond of that name because there are other things that can be flat also. Okay, so what if one of these substituent atoms was replaced by a lone pair? How would this change? Well, basically the only thing that would happen is that these two atoms would get maybe a degree or two closer to each other. And we just lose this atom that was out here. Okay? So we're going to end up calling that one angular or bent. I love the name bent. That's a great name for a molecular shape. Okay? And the type for that would be an AB2E. A is one atom. The two B's are the substituents, probably different. And E is the lone pair of electrons that goes right up there. Okay? So, a good example of that one might be PBI2, but to be honest, you don't encounter this all that often. Now, the AB4 is very different. This is tetrahedral. Rather than just putting them into like a T shape and have 90 degrees between them, if we go three-dimensional, this bond angle can become larger, which is about 109.5 degrees. Now you see I can pass my pen beneath this. is a three-dimensional molecule. Now, I remember the first time I went through chemistry. I was in high school, and I had slightly different views about things back then. And when my teacher started talking right away about these shapes, the first thing I thought of were these. And these are multi-sided dice. I was using them to play Dungeons and Dragons back in those days. I had a bag of them in my backpack, and I took them out to help understand the shapes. So this shape and this shape are basically the same thing. Okay, the top right here is this atom there. These three corners are these atoms here. The name tetra means four. Hedral refers to faces, so there's a face here, a face here, a face here, and a face down on the bottom. And I see the same thing here. One there, one there, one there, and a face that's down on the bottom. Okay, so that is a tetrahedron or a tetrahedral molecule. CH4 is a really good example of that. Okay, now I'm going to keep this here and show you what would happen if one of those atoms was replaced by a lone pair, which would be something like ammonia, NH3. Now, you had drawn these previously. If you go back over here to page number 4, there's NH3, there's CH4. Okay? So, when this happens, we lose the symmetry of the molecule. It's no longer symmetric. And the three remaining substituent atoms on the bottom end up getting pushed a little closer together, not a lot. The angle's about 107.5 degrees now, okay? And that varies from molecule to molecule a little bit, not a lot. And then if we go to an Ab2E2, this is what water would look like. Two lone pairs, kind of a Mickey Mouse ears looking thing here, okay? Two atoms, two lone pairs around a central atom. This is about 104.5 degrees between those substituent atoms. And it's the same thing here, where it was about 107.5. It's between the substituent atoms. Now, the name up here for the Ab4, this one was tetrahedral. The name here is triangular pyramidal. We need to say pyramidal rather than planar, because as you'll notice this time, my pen can go beneath the molecule. It's a three-dimensional shape. And this one, again, is called angular or bent. Great name, bent, isn't it? Okay. Now, to put 5 things around the central atom, you're going to have these two, which I've done in darker green, going up and down, which are 180 degrees from each other. Then you're going to have 3 that go around the middle, which are 120 degrees from each other, and are 90 degrees from the ones going up and down. Now the ones that go up and down are called axial, A-X-I-A-L, and the ones around, call that top and bottom. And the ones that go around the center are called equatorial. These go around the middle. Okay? Now, this is called triangular bipyramidal. So imagine that I've got one of these, 4-sided dice, again, this little pyramid, and another pyramid attached to the bottom of it. Okay. If one of these were to leave and be replaced by a lone pair, and we'll take one off the equator, we always do that, we get this, which the technical name is irregular tetrahedral. Nobody calls it that. Everybody calls it a seesaw, because it can seesaw back and forth like that. Okay? Bond angles are relatively close to the same. These might drop down by about a degree or something. Now, if 2 of them come off, okay, then what ends up happening is we get something that we call T-shaped. Okay? T-shaped. And if 3 come off, then we're back to a linear molecule. I have examples here for each of those. All right. Now, our next possibility is octahedral, or the octahedron. Now that has 6 things surrounding it. Not 8. It has 8 faces. 1, 2, 3, 4, and the same on the bottom. So octahedral is 8 faces. Okay? The bond angles are either 90 or 180 degrees. Like from here to here, that's 180. From here to here, that's 90. You get the idea. Okay? Good example of that is the SF6 molecule. And you drew the SF6 molecule back here on page number 5. Okay. Now we can take 1 off of that, replace it with a lone pair. We get what we call square pyramidal. We can take 2 off of it, get what we call square planar. These are rarer, but they do exist. Now, there is 1 molecule that I know of that actually goes pentagonal bipyramidal, which is an Ab7, and that molecule is IF7. Okay? So, what I strongly recommend you do is to make up some flashcards. And on the front, you would write something like Ab4, and on the back of the flashcard, you would put tetrahedral. Okay? Not that many of them to learn here. This will only be the second set of things this year that I actually want you to go through and try to memorize. Okay, that's going to take some time. You're going to get some homework. It's going to be called Lewis dots number 2. And what will happen is you'll draw the Lewis structures again, and then you will identify what their geometry is. Okay, thanks for tuning in today. This is Morgan signing off.